Are you familiar with the attributes of encryption keys? If not, well, then stick around. We're going to be talking about that coming up right now.
You're watching IT Pro TV.
Welcome back to Security Plus here at IT Pro TV, and today we are getting a little bit deeper into encryption keys. We've already kind of looked at the different types of encryptions that are available, but we need to get a little deeper, a little more nuanced when it comes to the keys that they generate. Wes, you're going to help us out with that.
Definitely.
Thank goodness, because it's kind of a bear to slog through, but very important for the Security Plus exam. So, Wes, where do we begin?
Most definitely. You know, in the last episode, we kind of left off with talking about the difference between symmetric and asymmetric encryption keys, right? We talked about key pairs, and you know, there were just some things that we couldn't really fit in that episode, so I decided that we would talk a little bit more, like Dan said, about the keys and go in a little bit more depth. So let's go ahead and start out with some basic definitions, right? So we talk about algorithms, right? What is an algorithm? Well, an algorithm really is nothing more than a mathematical procedure. It's an operation, right? Mathematical operation. It's applied to your data, and it defines how we go about encrypting information. And it's important to understand that the algorithms themselves, they are publicly known, right? When we say AES encryption or we say RSA encryption, right? That encryption is known. That mathematical operation is not known to me because anytime you put letters in math, I'm out. But you know, there is
right
some,
there with you, my
yeah,
friend.
there's some crazy math, and ladies and gentlemen, you don't have to know anything about how the algorithms are actually encrypting the information. So this is really just some basic definition. But it is important to understand that the algorithms, while they define how the procedure is supposed to happen, they don't actually implement the encryption. That's where the keys come in. All right, it's typically generated by the algorithm. You're going to see coming up when we talk about our public key infrastructure, we'll actually set up a PKI, and we'll show you the subordinate and the root CAs, and as we're generating those keys, we can define what the cryptographic service provider is. That is a big technical jargon for who's providing you with your asymmetric key encryption. What algorithm are you going to use, right? And then once we've defined what that algorithm is, the keys are generated. And then they are going to be used to encrypt and decrypt the information. The thing about the keys is, the key thing about keys, I just had to say it.
You're super punny today, Wes.
Yeah, that's absolutely right. Hall of Lame, is the fact that they make the encryption unique, right? So what, you know, if everybody knows the algorithms, right, or security researchers, they know what the algorithms are, then how does that actually help to keep our data confidential? Well, it's really about the keys. The keys are what makes that unique, that encryption instance unique to any data you send to me, if I'm using your keys, or you're using my keys, or the other way around, or any information that I'm sending to you, makes that in that unique instance of the encryption. So it is important to understand that more than anything else, the keys, they need to be secure, because the encryption, when Dan and I were kind of talking about this prior to actually shooting the show, and I was one security guru, and I'm going to say this completely wrong and horribly make a, not say it, just not going to say it right. Something about, you know, when it comes down to it, our encryption is only secure as how secure you keep those keys. If the keys are exploited, then the encryption, it's pretty much worthless.
Yeah, you got to keep those keys secure. It is one of the most tantamount concepts that you have to grasp about whether you have a symmetric key where it's just that one key that's going to be used throughout, or that private key in an asymmetric pair, keeping that secure. And I highly recommend that you kind of jump out there, find some tools that will allow you to generate keys, play with some keys, encrypt some data with them, decrypt that data with them. I think if you're in a Linux system, you can use something like OpenSSL to generate some keys. Super easy to play around with, and you'll start to see how, oh, make more than one pair, make 3 pairs. Play with those encryption algorithms, with those keys, make those things encrypted. Just grab some text files, encrypt them up, see how that works, kind of give you some legs to the concepts behind what we're trying to show you here. And you can start to see the differences in those keys, why they're unique, how they're unique, what went to making them unique. And that really will help solidify these concepts in your mind. Let's move on let's talk a little bit about key length, because this is an important topic for us to tackle and understand when it comes to these types of keys, right?
Most definitely. So key length is really determined by a bit size, all right? And you usually have longer keys or you have shorter keys, right? So to give you kind of some examples, right, we talk about bit lengths. You'll see some of these common bit lengths, 128-bit versus 256-bit, right? When we talk about all the possible combinations, right, let's start as the lowest one that I can remember, because 128-bit, when you look at 2 to the power of 128, that's really the same kind of comparison we have when we talk about IPv6 addresses. That is a number so astronomically large that if you converted each one of those possibilities into a grain of sand, it would take a container that's 1.3 billion times the circumference of our Earth to contain all those possibilities.
So big.
Big, absolutely.
Gotcha.
And that is the small key size by today, right? Today's computational value or computational power, right? You'll see 256, you'll see 512. When we talk about some of the keys that we generate inside of our PKI coming up in those episodes, root CA, because we want to keep it protected, has a 4096 versus the sub CA, which has a 2048-bit key, so 2048 bits in length. And it's important to understand that while longer is definitely going to be harder computationally to crack or break, if you will, shorter will be easier to break. And again, I guess that's all relative to the system that's attacking it, right? If you're trying to attack a short key with a Raspberry Pi, chances are it's going to be just as hard as anything else, right? So it depends on the resources that you have to throw at it. So shorter keys, again, lower resource requirements, right? The longer the key, the more processing power it takes to encrypt and decrypt the information. Same thing goes when you're talking about VPN communications. You have things like VPN concentrators, right? The higher you put that key, yeah, absolutely, you're going to get a stronger encryption. You're going to get a stronger security. But remember availability. The fact that it might the performance levels might be very, very slow. You might operate down at well, let's say the original Ethernet speeds. Again, because your endpoint devices, or actually your connectivity devices, are having to do that encapsulation, the encryption and decryption. And again, the longer those keys are, the more it plays into the resource requirements behind using that type of key length.
Wes, I think you're really hitting on an important concept when it comes to being a security analyst or a security professional. It's not just as easy as going, if it's the strongest encryption, that's what we're going to put on there. A lot of times that's not the case. Sometimes you're weighing the pros and cons, the risk factor versus the probability of something actually happening. If I've got some low impact data that it doesn't matter, I say doesn't matter, it might not matter as much as this data over here, whether or not it falls into enemy hands, I might use a lower encryption, give better performance, a better throughput, give my end user a better experience. Whereas if I have something like research data that is proprietary to our company, that's really important information that I would not want to fall into the competitors. And so I might use a stronger encryption algorithm, lose that performance factor, but I know that I'm keeping it a whole lot safer. So you hopefully you're starting to see that it's not always a black and white issue where we just use that strong encryption 100% of the time. It might just not be a good idea.
Sure. Think about IoT, right? Yeah. IoT doesn't potentially have a lot of processing power in these devices, right? And the SoC, system on chips, we're going to throw as many acronyms in this episode as we can at you, right? System on chips, they don't have a lot of processing power, but you still need these devices if they're doing things like remote telemetry. I don't want that information ended up in Dan's wireless protocol analyzer, right? I'm picking on Dan because I know Dan does penetration testing, but you want to keep that information secure. But at the same time, you can't throw encryption levels at that device that is really just the size of a credit card with some of these higher level encryptions because encryption algorithms because of the fact, or key links, I should say, because of the fact that it's just going to bog that system down. And then what happens is the functionality that the device is supposed to provide, it can't provide because it's spending more time than it is encrypting and decrypting information than it is actually doing the job that it was set in place to do. So great point too about, it's just not a one size fits all. It's really what one of our other security gurus says, Adam says, it's a one size fits one. It's a very tailored thing. That's why we can't give you every possible combination, every possible situation or scenario that you might show up on the exam, but then we can definitely, just make you aware of some more common ones.
That's right. Use as necessary, right? That's right. Now let's move on let's kind of go back to the conversation we talked about how important it is to keep keys secure, specifically private keys or symmetric keys if that's what you're using. But there will be times when I will need to exchange a key with someone, usually when we're talking about symmetric key encryption. That does happen. How do we do this securely? Wes, you've got some solutions for us.
Most definitely. So when it comes to key exchange, remember, key exchange is securely transmitting the key. All right, now, what is probably one of the most secure ways to transmit a key? SneakerNet. If it never hits the wire, it doesn't mean it's completely secure. I said one of the most secure. If I drop that thumb drive that key's on and it lands in the hands of somebody else, it's not completely secure, but this is a secure transmission of the key. Typically, in most situations or implementations, what we're talking about is we're doing communication across public networks, right? Networks that we don't own and we don't control. And we want to make sure that from end to end, that when we transmit a key, we do it in a secure fashion, that if somebody is out there eavesdropping on this key exchange, we can share something publicly, all right, come to an agreement and a common understanding of a shared key at the end of this communication process, and somebody shouldn't be able to derive what the shared key is, even if they've got whatever public information we shared beforehand, before we started doing encryption. All right, the endpoints are the ones that negotiate the types. Usually when we do a key exchange, we have a few different types. I told you about the SneakerNet version. That's what's called PSK. Do not let that confuse you. I know a lot of security documentation likes to use that. It's pre-shared key. All right, you've probably set this up on your home networks if you've ever installed a wireless router and you've put a passphrase on your network that people need to use to connect to your network. That is a pre-shared key. Why? Because I needed to know what that is and have that on the client as well as implementing it on the router, and we have to know it beforehand before we can make communications. That's pre-shared key. The other two, we've kind of talked about one. Well, we've really just kind of talked about both of them, but RSA encryption is another way that you can do key exchange. Diffie-Hellman is another very, very common one. You're going to hear that a couple of times throughout our series, especially when we talk about IPsec or Internet Protocol Security. Now, I don't think at this point we're going to talk about the different types of Diffie-Hellman. We'll come back here in just a few minutes, but we will have a little bit more to say about Diffie-Hellman coming up.
Oh, yeah, because now I'm super excited about your next slide, which is key stretching.
Yes.
Interesting terminology that comes about in the security space. So much fun to play around with. But this is the idea of actually, because it happens from time to time, keys become weak,
Yes.
or the encryption that's used can become weak. They'll figure out some ways to kind of strengthen these things back up,
Yes.
right?
Yep.
And this is the idea of key stretching.
Yeah, you know, so when we talked about encryption or we talked about hashing, one of the things that we talked about hashing was this concept of salting a hash, right? What are you doing? You're adding random characters to a hash and rehashing that value so that what you come out is this unique input or the unique output, right? And what does that do? It strengthens the salt, right? It's there to add to common passwords so that we can keep these hash values from showing up in databases that attackers are using to do brute force attacks, dictionary attacks, right? Well, let's talk a little bit about key stretching. So key stretching, I'd like you to think of it as a key strengthening. We're making the key stronger. Remember how the key is stored? A lot of times what this is going to be done against is this is going to really be done against passwords, right? Remember, we've already talked about password hashes. Remember when they're stored in a database, right? We have that hash value, and that's essentially what an attacker is going to try to exploit, right? So what it does is it inserts some random characters, and it increases the resiliency to a brute force attack. There are two types that I want you to be aware of. The first type is bcrypt, and bcrypt operates on the blowfish cipher, and the other one is PBKDF2, which is just password-based key derivation function 2. There's a version 1 and a version 2. I'm not sure if they're going to ask you that much in depth. Definitely be aware of this one. Let me show you a little bit about what something like this would look like. So let's say that Dan's working on a Linux distro, right, or a Linux machine, right, and he looks at that shadow file and we see something like this. It's not going to be exactly like that. It'll look different in the shadow file, but ultimately the hash is very small, right? Well, what we can do is we can use something like bcrypt. Now, I want you to understand, too, that here in this example, right, after we've done the key stretching, this is what it's going to look like. Now, I put the dashes in here so that we can make you visually aware of the components that we're looking at. The dashes probably wouldn't be in there after the key has been stretched or strengthened, if you will. All right, so what we have here is we have a hashing ID, and that identifies that, hey, the bcrypt hashing algorithm was used. Again, that's going to be a blowfish cipher. Then there's a cost factor. How many times do we run through this? This is up 2 to the power of 10, if you will. And then we have the salt that's added, as well as the hash value. Now, this is one solid string here. Take the dashes out, and this is what it would look like. And this is how we could identify that, yes, this is a key that's been stretched, really just starting out with those first few base 64 ASCII characters right there at the front would let us know, hey, this is one that's been strengthened with bcrypt, and we can see that by the ID. But just again, keep in mind that what it is about is more about making the hash values that you have more resilient to these brute force type attacks.
So just to be sure about this, we're working with hash values here. So that stretching is only for hashing, or is that also for like encryption keys?
It's typically for your passwords.
Gotcha.
Yeah, absolutely. It's more of a password-based type thing, which I always thought was interesting. They also say passphrases, and that's where the term PSK comes back. So technically, it could be considered a key. A lot of times, it's going to be implemented on passwords, and again, just to strengthen their resiliency to things like brute force attacks, dictionary attacks, some of those rainbow attacks that we've seen.
Good to know the context behind this. Thank you so much on
right,
that.
absolutely.
Now, you've mentioned a couple of gentlemen here throughout this series, one Diffie and a one Hellman. Can you explore the idea of keys when it comes to Diffie-Hellman?
Sure. So Diffie-Hellman, you might hear it or see it abbreviated DH. This is a key exchange algorithm that essentially it goes back to the 70s. It was invented in 1976, and it's kind of interesting. This whole process of Diffie-Hellman and the asymmetric key encryption actually started as a way to verify proof, if you will, code that was running our space shuttles during the NASA programs, right? You don't want to be in space to have to debug some of your software, right? You want to make sure that you can validate that software has maintained its integrity, and according to Whitfield Diffie, which meant including that it was bundled with all of its bugs as well. But that's what originally it was designed for. But what this does is this allows you to securely generate a master key, and it helps you, it's resilient to these man-in-the-middle attacks. There are different variations of this. You will see DHE, which is the Diffie-Hellman encryption standard. You will see elliptical curve cryptology, all right? Now, when we talk about ECC cryptology, remember that these two, one's going to require more processing power. That's the old DHE. Anytime you're using ECC, whatever it's attached to, what it says is you can reduce the key link size, which means what? Less processing power, but still have strong security. And that's why the elliptic curve Diffie-Hellman ephemeral is one that's most common to. Ephemeral just means that the keys are going to change. Again, the session keys are going to rotate. Again, the concept of an ephemeral key means that you have it, you've captured it, that's fine, but what you've captured is useless to you now. It's only good for that one piece of data during that transmission. And we've got, like Dan said, computers are fast. We've got hundreds of thousands of transmissions that have just gone on within a few seconds after that, and each one of those have new keys. So the likelihood of you gaining access to all the collective keys and reconstructing the information so that you can make some sense out of it, I won't say never, but it's highly unlikely. There are some other things that I want you to mention out. There are also some Diffie-Hellman groups. Make it easier for yourself. There's all different numbers. The higher the number, the stronger the stronger the Diffie-Hellman group is. It's basically what you want to know about Diffie-Hellman. We're going to talk a little bit more about Diffie-Hellman because it is one of those concepts. Not only do you see it in cipher suites, but you also see it in things like IPsec as well. So that's a little bit about the Diffie-Hellman algorithm, and be aware of it for the exam, and definitely be aware of some of the attributes that we've talked about it right here.
Yeah, another concept that would probably be good for us to be aware of is key management. How do we work with these keys a little bit, and what are the common practices that we'll go through as we basically work with keys?
Most definitely. So if you think about it, key management is just the process. I know, wait for it. Managing cryptographic keys. All right, class dismissed.
Man,
just kidding.
easy.
That was really easy, right? It's a little bit more than that. Some of the key management activities that you can see across the key life cycle, you've probably, and you'll see us actually do key generation coming up later on in the PKI episode. So key generation, key exchange, we've talked about things like Diffie-Hellman, pre-shared key, If it is a public key cryptology, how do I get the public and private keys over to the endpoints? Typically, we can do that by issuance of certificates. Other things like usage, what do we use them for, right? We'll have an episode coming up on things like certificates and what we use these certificates for. So for instance, if Dan spins up an Apache server or maybe a LAMP server, LAMP stack, and he's out there on the internet and he's serving up web pages, right? I want to be able to, or he wants me to be able to trust his website when I go to it, right? Well, he's got a server certificate up there for a web server that has those keys, and it defines that that is used for server authentication. That would be an example of usage. Code signing, right? Things like not just client identification, user identification as well, too. So usage is definitely important. The other thing, too, is things like storage. How do we actually store the keys? Things like renewal. When that validity period comes up and those keys actually have to expire, do we renew them? And again, there is no right or wrong answer here. Maybe we let them expire. Maybe we have some kind of certificate renewal process where we regenerate the keys, or we just extend the validity period, if you will. It could be the fact that we need to archive these. So you'd say, well, why would I want to archive a key? Well, I want you to think about, we talk about in many of the other shows that we have here at IT Pro TV, if you're not aware, when a person leaves your company, right, you disable their account. You don't delete the account, because if you delete the account, anything that person had access to, all the files that they created, all the files that they encrypted, well, you delete the user, now all that access is gone. So if a user has used their public key to encrypt, and the private key is the only thing that can decrypt that information, well, what happens if we let that user go? So what do we do to the key? Well, you don't destroy it, because if you destroy it, which will be the last process in the key management activities you'll see here, you no longer have access to the encrypted information that's within that data. You'll lose access to that information. So things like archival, recovery as well. We have things like KRAs, key recovery agents, right? If a key gets corrupted, how do we gain access to the encrypted information? Well, a key recovery agent can facilitate with some of those actions as well. And then finally, last but not least, is destruction of the keys. This is a term that's called crypto shredding. You can see this, you don't need a big, large infrastructure. For instance, TPMs, we'll talk about those a little bit later, but again, a little trusted platform module that holds cryptographic keys in the motherboard itself on the systems that it's part of. Well, if that gets tampered in any way, guess what? That little TPM says, uh-oh, somebody's trying to tamper with me, and shreds all the keys so that nobody can gain access to the information that those keys protect. So destruction of the key as well. The last one, be careful. Remember, if you destroy a key of something that's been encrypted with it, you no longer have access to it. It's like basically removing the lock from the front door, but there's no handle there anymore. You can't get into the front door anymore. So there you go. Those are some of the key management activities I'd be aware of.
I'm thinking of total protonic reversal. Right?
Absolutely.
Right. Distraction. Don't cross the streams. Bad idea.
That's right.
Well, we looked at a lot of information today when it comes to keys. A couple of things we went through are things like the algorithms, the keys themselves, key length, also very important. Stretching was an interesting topic of conversation. And of course, management, how do we work with them? Very important concepts to be aware of for the Security Plus exam. Out of time for this episode, but more to come still in the Security Plus series, so join us then. Until then, have a great day.
Thank you for watching IT Pro TV.